Hello, and welcome back to Two's Complement, the program where we translate the One Lone Coder's pixel game engine from C++ to C#. My name is your host, Propagating. As always, I want to give a huge thank you to JavidX9 and his One Lone Coder project for allowing the use of his pixel game engine in this series. And while we're not endorsed or in other ways supported by JavidX9 or by his project, without his permission to use his code for this, we obviously wouldn't have a series at all. So a huge thank you to him, and links to his social media / YouTube and GitHub are in the links below, as well as on the GitHub for this project. With that, with the niceties out of the way, we can go ahead and get started on this week's episode. Apologies that it took a little bit longer than anticipated to get this out. I was trying to work out the best way to split up our episodes for for this next bit of translation that we'll be doing. So what will we be doing? Well, as you see on screen, we have the resource buffer and the resource pack, and that's what we'll be focusing on over the next 2 or 3 episodes. So what the resource pack is, as you can kind of see from the comments on screen in the source, is essentially a way for you to combine multiple smaller files into one larger faux file system for use in your game. If you look at other games, you'll kind of notice that they don't usually come along with, the thousands of resource files like the sprites and textures and other things that they need to display the game. What do they have instead? They have usually a couple larger proprietary file systems that contain all the files that they need for the game, and they're organized in various different ways. And that's essentially what our resource pack and our resource buffers are. Our resource pack is the file itself that contains all of these smaller resources, and the resource buffer is how we load those individual resources into memory for use, either displaying our sprites on screen, playing an audio file, things like that. So what we'll be doing today is going over the creation of the resource packs, adding files to it, saving the pack and loading the pack to memory, as well as getting the resource buffer loaded for a specific file as needed, or multiple resource buffers in this case. We will not be going over the scrambling methods. Scrambling in this case is a form of encryption. That will be talked about in one of our future episodes, just because in order to achieve this in C#, it's going to be a little bit more involved and a little bit different. And so I want to spend more time talking about how we are going to achieve that. And I really want to kind of dedicate some time to how to kind of get secure encryption of files and unencryption of files while keeping things in memory and things like that, because I think that'll be an interesting topic. I know I've definitely learned a lot as I've been kind of researching and practicing that. So we'll be doing that in a separate episode. So today, like I said, we'll be going over the creation of these resource buffers and resource packs, and just by looking at what they make up, they're pretty simple classes, right? So the resource buffer itself seems to inherit from a stream buffer of some sorts, and all we have really is a constructor, and we have an array of chars or bytes, whatever you want to call in C++, that are the same. So we have an array, or a vector of memory, a vector in this case, so it can be resized, that holds the raw byte data for the file that is read into memory. And this can then be passed around to our image loader, audio loader, whatever else, assuming they can load from a byte array. So that's pretty straightforward. That's a resource buffer is not going to be a difficult thing to do. Our resource pack is a little bit more involved. Obviously we have like some basic constructors. Whoa, okay. Sorry, my cat decided to stand on my keyboard. That was interesting. So we have our basic constructor and destructors. We have adding files to the resource pack, loading and saving in the pack. We have pulling a file or getting a file buffer from our resource pack, and then we just have a simple function that tells us if a resource pack is successfully loaded or not. Obviously, when we want to tell if it's properly loaded or if it's been disposed of before we try to read from it for error handling. This is made up of a dictionary of files that has a file size and the location that the file is stored in our pack. It has our file stream that is passed around, so that way we're not constantly disposing of and then recreating a file stream. And then we have a method to scramble our data, or encrypt it essentially in this case. And then we have a helper method to make it a POSIX compatible path, which we don't need to worry about in C#. With the we don't need to worry about the path formatting. C# will kind of do that for us and support whatever kind of path formatting that we like. So without further ado, let's go ahead and get started. But before we get into the C#, I thought it would be helpful if we talk a little bit about how the resource packs are formatted with a visual. And I kind of talked about this a tiny bit, or if you the astute among you might have gotten the idea from the dictionary that I had mentioned. So what I have on screen here is essentially what our resource pack looks like. So what we have here is kind of our, think of this as our this is our kind of file representation, our resource pack, which is just stored on disk as a binary file. If you wanted, you could create a proprietary file format for this and register it, and all that fun stuff. It's not really that important how you store this. The formatting is going to be essentially the same. So what is stored inside of our resource pack? The start of the pack has the total size of the resource pack as a whole. This is more important for the C++ side of things, where we don't have some kind of built-in helpers for telling us when we need to stop reading a stream. So that's where this is kind of beneficial. It kind of tells us where to stop reading. Next, we have a chunk of memory that is our index entries. This contains our file names, the offset of where the files live in memory, and then the size of those files, again telling us how much we need to read per file. Following that, we have all of our files kind of in sequence. And what this sequence is really up to you, depending on how you add your files to the dictionary. And essentially how this is laid out is, where the file begins is the file offset, right, as we have right here. We have our file size, essentially, which is, from file 1 offset all the way to the end is our size. Boom. And at the end of that, where file 1 ends is kind of where our file 2 offset begins. So, we just have our files kind of all the way along, filling up the whole file. We don't really have any empty space here. That's just how it is. And our index entries are going to look like this. And I'll talk a little bit about why we have our, why this data size is important. So as we kind of are writing our data file or our resource file to disk, we're not going to know exactly where our file offsets are going to be until we're actually writing the file to disk. So we'll need to update our index with our offsets kind of after the file's been written. Now, we could maybe pre-calculate what offsets our files are going to be, But in order to pre-calculate that, we need to know quite a bit of information. For one, we need to know the size of every single index entry, which is where we kind of get into our data size. We need to know that our order of our files is always going to be the same and it's never going to change. And we need an accurate representation or an accurate knowledge of the length of our files. And some way to ensure that that length is not going to be changing. Now, when you are kind of writing a game in this engine, ideally, once you're packing these resources for the final time, all of that will be known. That said, the efficiency that we get from pre-calculating where these offsets are, instead of writing and then updating, the index with the offsets, is very minimal, because you're not going to be packing resources while after the game has been delivered. Really, you're packing your resources prior to delivery of the game, and the end user is never going to be running this pack resource or the save resource method. They're only going to be loading resources from disk. So it doesn't matter as much if we have a little bit of inefficiency here in updating our index. Nonetheless, if you did want to pre-calculate the size and offsets of everything, you need to know the size of each of your index entries. And they're going to look a little bit like this. So first things first is that we have a file name. And it's important to note that when you're writing a binary file, because that's essentially what this is, when you're writing a string, you need to prefix the string with the length of the string. And that's because your string can have different encodings, and depending on the encoding used, it's going to affect the data size or how much space that string takes up. And we can just run a real quick example in LinkPad to see that. And I've already run this on string. I've already run this test before, but we can run it again. So here we have a string, that's 20 characters long, and we're just outputting the length of the string and the size that the string is going to take up depending on the different encoding. So if we use UTF-8, which is pretty standard, it's just 1 byte per character, right? It's 8 bits per character, 1 byte. Same thing with ASCII. But if we were going to use Unicode is UTF-16 or 2 bytes per character. It's going to be 40 bytes for this string. So it's the length times 2. Now, because our file names could be fairly long, the encoding for us isn't going to matter. As far as I know, most systems are not allowing you to use emojis and things like that in your file names, so they should be plain text. So we should be safe using UTF-8 encoding, just to be safe. Possibly using ASCII, although with some languages, I think ASCII is not going to have all your characters. But that's kind of, it's up to you, which encoding you use at the end of the day. So that's just something to keep in mind. Coming back to our index entries, right? So we have our file name length that needs to be stored, so that way when we're reading the file name, we know how many bytes go into the string. And this file name length is the size of this length could change in memory, right? This could be as small as 1 byte, assuming our file name length is less than or is able to fit inside of a single byte, or is less than 255 characters, or it could be as much as 4 bytes. I don't believe Windows will allow you to have a path length or a file path length that is longer than the 16,000-ish characters, I think it is, or no, 65,000 characters in a short or a 2 bytes number. So Ideally, this should really be between 1 and 2 bytes in size for our file name length, but we'll just say 1 to 4 to be safe. Then we have, the actual length of our file, and that size is again the length in the number of characters times the encoding kind of modifier, which we just looked at. Assuming we use UTF-8, this is just going to be the length times 1. Then we have the offset of where the file lives in memory. In C#, the offset is technically a long. However, we cannot have a resource file that is greater than 2 gigs. It's kind of limited to the size of a signed integer. So for the sake of, kind of keeping with that convention and for the sake of simplicity, we're going to assume that all of our resource packs are going to be within the 2 gig limit. As such, our offsets and our positions are going to be integers and are going to be 4 bytes. I will leave it as an exercise to the reader or the watcher if you want to implement some kind of streaming and have larger than 2 gigabytes resources or resource files. But as it stands in the Pixel game engine and in our C# translation, we're going to be using integers for this, 4 bytes. Same thing with our file size. No independent file is going to be larger than 2 gigs, and hopefully they'll be much smaller than that. So our data size for that is going to be 4 bytes. So in total, we will have a minimum of 4, 8, 9 bytes plus the length of our file name. So this is, anywhere from 9, assuming, let's say 255, so 9 to 264 bytes per entry. Obviously, this could get much larger depending on our file length. And you'd need to calculate that for each other thing. I've kind of spent a little bit too long on this. Apologies for that. As you know, I do ramble a little bit sometimes. But hopefully this gives you a much better understanding of exactly what this resource file looks like and what we'll be aiming for as we're creating it. So with that, we can go ahead and move over to our C# code and start talking about our implementations. So first things first, let's go ahead and we have our resource buffer class, which has been created already. So again, we have a byte array, which is our buffer, and we have a constructor. In this case, this is taking a stream offset, a stream object, and it's pulling a data offset and the size of our data to read from our stream. So first thing we do is we're initializing our buffer, and we're setting it to the size of the file that we want our buffer to contain. We are going to go to the offset location in memory. When you seek a location from a stream, you can choose where you want to seek from, if you want to go from the beginning or the end. All of our offsets are going to be from the beginning of the file, so we're saying our origin's at the beginning. We'll seek to the beginning of our data, and then we'll read our bytes into our buffer. The only interesting thing here is that this offset is not the offset in the file, right? We went to our offset location using our seek function. This offset here is talking about what position inside of our buffer we want to start writing at. This is our write offset, not our read offset, if you want to think of it like that. So we want to write the data at the start of our buffer, so position 0, and how much data we want to write is our data size. So that's easy enough. That's what our resource buffer is doing. It's reading our data from our stream object into our byte array, which we can then pass around to other objects. Next, we have a resource file, and if we just go back to our source code real quick, that's what this struct is, and you see all this has is a size and an offset, and this is used in our dictionary, our index of files. So that's all that we're doing here. This is super simple. Again, we just have a size and an offset and just some constructors here. The reason I have two constructors here is that when we create our resource map or our index, that the dictionary that's going to hold our indexes, again, we're not going to pre-calculate our resource offsets, so we're not going to know them right off the bat. We're not going to know them until the file's written to the resource pack. So when we first create them, our offsets are all going to be 0, and then later we will go back and update our resource offsets to their appropriate to the appropriate offset, and then write that to the file. So that's why we have two different constructors. Now, yes, this is a struct. It's a value type, so updating it in place is, a little bit different. This didn't necessarily need to be a struct. It could be a class. I decided to keep it a struct. It takes, a very small amount to actually update this value in our dictionary and just replace it. So it's not a big deal, but, I do recognize that we will be kind of updating this in place, and need to do that because it's a value type, not a reference type. Not super important. I'm just calling it out ahead of time. Next, we have our resource pack itself. So our resource pack is fairly, the fields it has are fairly straightforward. What do we have? We have our public dictionary, which is that index that contains the name of our file, the file size and offset. We have the stream object that we're going to keep open and pass around, so that way, again, we're not opening and closing streams all over the place. I did add a new field, which is a salt, which is going to be related to our encryption stuff. Again, we're not going to talk about that in this episode. I just decided to create a salt. Obviously, when you make it, set it to something else other than mine. But it's here for later. We have our constructor, which is setting, just creating a null resource stream. We don't want to create a stream that is totally empty and reading nothing to begin with. So this is just going to be null to start out with. And we are initializing our file map just to make sure that this is, an empty dictionary instead of a null dictionary, in case we, try to access this before it's been initialized and get a null reference exception. Or something to that effect. So, with that said, let's get to our implementation. So first things first, we need to add, we have our function to add the file to our file map. This is super straightforward. You pass in a file path. I'm doing a very basic check to make sure the file actually exists. It should exist if you're putting in the path, but better safe than sorry. We are getting the file info in order to grab the file length. Again, this is stored as an integer. Normally file length is a long, because technically you could have files larger than 2 gigabytes. But I am trusting, maybe foolishly, that the users of this will know that their resources cannot be larger than 2 gigs, and as such, I'm casting this to integer, because that's what we're using. So, maybe this is a little foolish. Maybe it's a little kind of we're being too trusting of our end users, but it is what it is. And then we're just adding we're just adding our files to the dictionary with the file path and our resource file type as our value. And assuming this succeeds, we're just returning true, indicating that this was a successful operation. Next, we will go and talk about, not this, this is for our encryption. We'll talk about saving our file to disk. Now, first things first is that we need to create a new file stream. And what this is going to do is it's going to create a new file, or if an existing file with the same name already exists, we're going to open it and we're going to overwrite it. I'm not going to worry about, I'm not going to worry about overwriting the file or, make a user confirm it or anything like that. Again, this should be something that, you are doing on purpose. So, that's why I'm just allowing this to overwrite the existing file or create a new file if it doesn't exist already. Next, we are going to create a new binary writer. This is going to give us some nice extension methods in C# that are fairly easy for us to use, and it's going to simplify things like writing the strings to the binary or to the file without needing to worry about calculating the length of the string. It'll do that for us and write and prefix that length, so we don't need to worry about that bit of code, which is nice. It's a nice simplification that we get in C# that we didn't get in C++. Next, we're writing our starting position. This should be 0 for most cases. This is going to be a little bit more important when we talk about the encryption, where the start position could be non-zero, but in this case, it is going to be 0. So this is going to prefix us with a 0 when we write our data. And next, we're going into another function that is writing out the data itself in this write binary data function. I split this apart again for the encryption side of things to reduce code duplication. So that's why it's a separate function. And here we can talk a little bit about how we're actually writing our file or writing our file data. So first things first, as I mentioned, our binary writer automata is going to know, or it's going to get the size of our strings. So we don't need to calculate the size of our strings and write that out. And we also don't need to say, how much space we need to write specific data. It will kind of do that for us. So first thing that we are going to store, though, is we are going to write out a holder integer for the size of our resource file. And if you remember on our diagram, the first position that was written was the size of the resource pack. That's going to be written in our first position, all right? I'm sorry I misspoke earlier. It's not our start position. It's the size of our resource file that is going to be written. This is going to be a 4-byte integer that is just 0 to start with, and we will update this after the fact. Next, we are going to write the size of our file map, or the number of entries in our file map. So this is essentially how many files are contained within our resource pack. This is going to be useful for when we are reading the resource pack back into our class, so that way we know how many files to expect outside of that load. And we're going to write that map size to disk. Then for each of our files in our file map, the dictionary that we previously discussed, First thing we're going to do is write the file name, which is the key. In this case, it's the dictionary key. So that's how we access it. Again, this is a string, but because of how the binary writer is written in C#, it will automatically prefix our string with the length of the string, and then we'll write out the string itself. So we don't actually need to worry about calculating the size. Now, I believe there is a write. No, there's not an actual write string method. It's just called write in this case. So we will just write it. We'll just write it out. You'll notice, the write method has a bunch of overloads for the different data types that can be written. You could say write. Oh, I'm sorry. Yeah. So this is a bunch of. I'm mistaking the read and write for a second. My apologies. But essentially, the write method just has a bunch of overloads for the different types. So we don't need to specify the type of data that we're writing unless we're trying to write 7-bit encoded integers, which we're not. And I'm not going to get into what those are because we're not using them. So that's why we don't need. That's why you don't see us kind of defining the types here. So we write our key. We write our resource size. And next thing is we are going to write our offsets, but remember that our offsets are 0 right now. We don't know what our offsets are going to be until after they are written to the file itself. So in order to update, our offsets after the fact, we need to store the position that the offsets are going to be stored. It's kind of the offset, if you want to think of it like that. And that's essentially what we're doing with this resource keys dictionary. So we're creating a new dictionary. It's going to have the name of the file, and it's going to have the position in memory that needs to be updated when we have the resource offset. And this is where our start position comes into play. But again, our start position is 0. So it's really just the current position of our file stream. So again, right now, for our resource offsets, we're writing 0, but we're also writing the position of this offset to update in the future. Okay. And then we're doing this for each file. And at the end of writing this bit for the file, we're just flushing the write buffer to disk, just to make sure that, everything is written properly. I don't really actually think I need to have a flush here. It's kind of a habit that I have picked up to make sure that everything in memory is actually written out to the file in small chunks instead of to writing, a very large amount all at once. So once this is done for each file, our index is written. Fairly straightforward. Next, we're storing our current position in memory, or we're just kind of pulling our current position in memory. And this is going to be to start calculating the offsets for our files and for the file data. So now again, for each of our resources inside of our file map, now we need to write the actual file data of those resources into our resource pack. Just real quick, if you need to reference it again, this is the actual data, the file 1, file 2, etc. data that we're writing into our resource pack at this point in time. But before we actually write the data, we need to write our current position to our offset dictionary that we had created. So that is what we're doing here. So we are updating, So what we're doing here is this is where we are updating the offset of our files inside of our file map dictionary. So essentially what we're saying is we are pulling our resource file struct from the dictionary. We are updating the offset with our current position, and then we're just updating, or we're rewriting that to our dictionary. Essentially, this is updating our offset value, so that way in the future we can go back and rewrite the offset. Sorry, I don't have a good way of saying that without saying offset a lot. This is just, we're updating where the file's been stored now, so that way we can properly write that value in the correct place in the future. Next, we write the actual file data to our resource pack. We update our position. We flush the data, again, just to make sure that we don't have this huge amount of data in in the buffer that is not actually written to disk, and then we clear out the buffer by flushing it. This is probably a little bit more important to do here than it was previously. And we do this for each of the files. We update the offset that we have stored. We write the file data, we flush, we go back and do it for the next. At the end of this, we now have finished writing the kind of first pass of our entire resource file. And we know the size of our resource file. So what do we need to do now? Now we need to update the resource file size, and we need to update the file offsets for each of the files that were written. So we're going to go back to the beginning of our file. We're going to seek our start, which is seeking our start position. In this case, it's position 0. We are going to write the resource file size, which is the size of our entire file at this point, which is the same as the length of our stream. And we know, because previously this was written as an integer, we know that we're not going to be overwriting something that we don't want to overwrite. Because when we wrote 0 earlier, that 0 was an integer, so we know it was 4 bytes. We're overwriting 4 bytes with another 4 bytes. There's no overlap happening. Lastly, we are updating, this is where we actually update all of our offset positions. So what do we do? For each of our resources, we use our resource key dictionary to find where our offsets are stored, and we seek to that position, we write our new offset, and we flush to disk. At that point, our file is now complete and has been written successfully, hopefully, to disk. Assuming all this worked fine, we return true, showing success. If we really want, we can write that. We can throw this in a try-catch block, return false on exceptions. That's probably good practice. I will do that in the future. For now, as far as this is concerned, this is fairly straightforward. We're just going to return true. And if an exception happens, it'll error out. But, we will update this with some additional logging and error correction in the future. Okay. So that was a lot of talking to save the file. Now, thankfully, loading the file is going to be much easier. And the reason this is going to be easier is that we don't need to load every single file into a resource buffer when we load the resource pack. The reason being is that we don't want to load things into memory that we don't need, right? So this is where your organization is going to come into play when you think about using these resource packs. So say like you have a resource pack for every level, or a resource pack that is only your textures. Maybe this is a better example. So let's say that that's how I have this organized. I have one resource pack for all my sprites. I've got one resource pack for all my backgrounds, one for all my, maybe I have one for my audio, something like that, right? I only want to load into memory the files that are immediately needed and maybe prefetch a few others, right? So it doesn't make sense to load every single file immediately when I load my resource pack. All I need to load initially is my file map. And my file map is going to tell me the name of the file. It's going to tell me where that file exists inside my resource pack, and it's going to tell me the size. And with that information, I can then create a resource buffer that actually loads the file, for the files that I need. So what do we need here, right? All we need to do is, again, we need a file stream, and we're going to use a binary reader. I have a couple options set up here to make this a little bit easier to use and will not brick our access to our resource pack if something goes wrong. Again, we'll do some error correction and some error handling kind of in the future. I think I'm going to have my own kind of separate episode on doing that kind of down the line. I know it's kind of bad practice and creating technical debt not to do it now. However, I'm trusting, again, maybe foolishly, that my end user has enough domain knowledge to kind of avoid errors as they write things. But, we will hopefully temper that foolishness on my end in the future with additional error handling. No, it's the last time I'm going to talk about this, I promise. But I know that, somebody's going to mention it at some point. So our file options here is we're only opening the file. We're not going to create a new file or anything like that. We need to open an existing file. So if the file doesn't exist, we're returning false, meaning this is not loaded at all. We only need read access. We don't need write access to the file. And ideally, when the game is loading these, nothing's being written to these resources. They should only be read from when the game is fully deployed. There should be no writing again at that point. There is kind of some built-in caching that is done for depending on how the file is accessed. And because we are loading different files from different places in our resource pack, that's considered random access, right? We're not always reading this file sequentially. The resources that we're loading could be in any order. So we want to set this to random access so that way if there's any caching that goes on for loading the data, it's kind of optimized for random access. And by setting the sharing option to read, it means that we're allowing other file streams to read from the same file. And ideally, that means if we really wanted to, we could have multiple file streams reading at multiple times and accessing this the same file for maybe some kind of multi-threading or parallel loading of data. Our next thing is we are processing, or we're creating our resource stream here. And this resource stream is what is going to be passed around to our resource buffer when we're loading it. And this resource stream is going to be alive for essentially as long as the application is alive. And the reason being is that the thought process behind this is that you will want to be loading multiple resources from the same resource pack over the lifetime of the game. And because of that, it just makes sense to have the stream open over the lifetime of the game. That way you always have it ready to go when you're loading, when you're ready to load a new asset. There is maybe a potential issue here if you have a ton of resource packs that you want created, and you have a ton of resource streams. I think that's a relatively non-issue here. Again, this is maybe going to be up to, the implementation of the user at the end of the day. But for now, this seemed to be the better or the best way of going about keeping a stream alive. Granted, that said, opening a stream in C# is fairly lightweight, even if it is opening, from disk. So this may not be as necessary as we think it is, or as I think it is. But it is how it's done in the original Pixel game engine, and I want to emulate that functionality fairly closely. So this is how I'm going to go about it. You'll notice that this resource stream and the binary reader are not in using blocks, so these will not be disposed of when it goes out of scope. These will stay open, once they're out of scope. Yes, even the binary reader will stay open, because if the binary reader is disposed of, oops, my apologies. If the binary reader is disposed of, it will dispose of the underlying stream, which means it will close our resource stream as well. So that's something that we really need to be careful of. So that's why we're leaving our binary reader open in this case. It does not cause any problems down the line. And it's not like a huge memory loss to keep this open either. So what are we doing? First off, we're reading our file size. This is, again, the first field inside of our resource pack. This is actually not really used in our case in C#, but, for the sake of, cross compatibility, I know I said I wasn't worrying too much about it, but this will exist in kind of the existing resource packs. So, ideally we could read a resource pack from the C++ version as well. The first thing is going to be our file size. Next thing is going to be our map size, the number of files that we need to read. And then we just read that number of files into our file map, into our dictionary. So first thing is we're reading our resource name, which is a string. And again, this is going to automatically read the size of the string and then read that many bytes into our resource name. Next is our resource size, which is an int32. And then is a resource offset, which is another int32. One difference here is that the original Pixel game engine has these as unsigned integers. These are not unsigned integers in the C# version, which is going to wreck possibly our cross-compatibility, although they should never be negative in the first place. They should always be positive. But it might impact cross-compatibility a little bit. Again, these are signed in C# because the limit is 2 gigabytes. It's not 4 gigs, so that's why these are left as signed integers. In theory, we could make these unsigned. Again, there's arguments either way. Maybe it does make sense to make these unsigned for cross compatibility though. But for now, for ease of use, they're just signed integers because that's what C# is using for the most part. So we're reading our fields we're reading our fields, and then we're creating a new resource file and adding that to our file map. And then we're returning our loaded function. Loaded is a true false, and it's basically saying if it's loaded, it means our resource stream is not null, which means it's initialized, and we are able to read from our resource stream. Ignore this transform key. This is for encryption, which again we'll talk about later. So assuming that our resource stream is not null and we can read from it, then it means it is fully loaded and we can get data from our file buffers. And that's the next thing to talk about, because we've just read our data from our we've just loaded a resource pack, and now we can get a file buffer if we need it. So our get file buffer is real simple. We check if we're loaded. If we are loaded, we return a new resource buffer. We pass in the stream, our file stream in this case, which we've kept open for that reason. We pass in our offset, and we pass in our size. And that's it. And then, again, from our offset and size, we initialize a new byte array. We seek to that offset, and we read the data. Easy peasy. Now, let's see this in action, okay? So what I have here is we have, a very simple program to read the directory of our project and write all the files in that directory to a resource pack. In this case, I'm just calling it testpackraw.txt. This doesn't actually need an extension. I'm calling it .text just for ease of viewing. It could just be no extension. It could be .bin, whatever I want. It doesn't really matter in this case. I'm just going to leave it as .text for now. I'm going to read in the files here. There are 5 files in the core folder. There's our project file. There's our core configuration, core engine, the Pixel Game Engine header, and our program.cs file. So we should expect 5 files to be output. I'm going to save that. I'm going to immediately load it. And then for each of these files, I'm going to load it into a file buffer. I'm going to write the length of that buffer. I'm going to get the file info of that file, and I'm going to write the file to my desktop. And then I'm going to just write out to the console that we successfully wrote to disk. And once this is done, we're going to look at the test pack data and see if it looks like we expect it to look like, and we're also going to look at the files to make sure that they're output correctly. So I'm going to run this in debug mode for now. Now this should work because I have tested this previously. And according to this, okay. So according to this, we're good. So we wrote our core configuration, which is 398 bytes to disk. We wrote core engine, 472 bytes. We wrote the Pixel Game Engine header, which is 246,000 bytes. We wrote our project file, which is 308, and we wrote our program.cs, which is 4,287 bytes. Now, let's see what this looks like on disk. So let me pull up. Well, I'm gonna pull this up in a hex editor view for now. Just because it's going to give us access to the raw data and some other information that we want. So here I'm using imhex or imhex, which is a free tool. You can find it on GitHub. And we have on our left here, we have the raw byte data that is written. And on the right, we have the representation of that data. So you can see here, again, because this was just raw text for a lot of this and, essentially numbers, we have the raw text on the right. And just taking a look at it, we see that on the right-hand side, we have the file path of our files, and those look correct. We've got our core configuration, our engine, the Pixel Game Engine header. We have our project file. We have our program.cs. And after that, it looks like we've got a namespace, and we have the data of the files beneath that. So this, at cursory glances, this looks correct. So now let's look at these values and see if they match up. You'll see that I have up here, on screen, I also have the properties of the file, and we see here we have, the size on disk is 252,109 bytes. So let's grab these first 4 bytes of our data. Look at our int 32 and our unsigned int 32. You'll see that they're both the same, and you'll see 252,109. So yes, that's what we expect. Our next 4 bytes is 5. And what is that? We've got 5 files being written out, or 5 files inside of our resource pack, and 5 files that were written out to the desktop. And yes, we have 5. Okay, what's next? Next, we have 1 single byte. And this is 42. And this translates to 66. And this is where, if you'll remember from our earlier view of the file data, that the size of our string file path could vary, right? It could be anywhere from 1 to 4 bytes. In this case, because it fit inside of 1 byte, it was less than 255 characters, it was stored as a single byte. So in this case, we've got a 1 byte length for our string length, which is 66. And the next 66 bytes are the string length of our of the first file. Okay, so next we should see 4 bytes for the offsets. I'm sorry, for the size, not the offset, for the size, which is 398 bytes. And if we look at our console, we can see we've output 398 bytes for the length of the file. That looks correct, yes. Now, we can go to the offset. This looks like offset 370. So let me go down to offset 370, which is going to be... I don't know what 370 is in hex. 1 second. Decimal 370 in hex is offset 172, 171, 172. Yes, 172. Name starting with namespace pixelsharper.core public read only struct. This was our core configuration class, so let's look at core configuration. Oh, look at that. Namespace. Oh, let me go back to our writer window. On our writer window, yep, starts with namespace, pixelsharper.core, and so on. Okay, so if we go back to hex and we look at, well, I'm not going to count out 398 bytes, but I will tell you that at 398 bytes, yes, we do actually get... well, actually, we don't even need to do that. You know what we could do is we could just go to... we could look at the offset for the next... We could just go to the offset of the next thing, right? So next is our core engine, right? Which has a size of 472 and an offset of 768. So let's 768, which is hex 300 on the dot. How about that? So hex 300. Oh, wait. No, I lied. That is... 768, correct? Yeah, 768. 300. Oh yes, here we go. I don't know why. I don't know what I was looking at. I'm sorry. But we have the same thing. Namespace, pixelsharp.core, and so on. So it looks like we're good. It looks like our offsets were written correctly. Our sizes were written correctly. Our overwriting of the, or our updating of the various sizes and places all worked. So to me, that's a success. We have saved our resource pack to disk. We have stored 5 files inside of our resource pack, and we have been able to pull those files back out. And we've been able to load them into our buffer, get information from them, and again, write them to disk is needed. So I'm going to call this a success. We've successfully started, we've successfully achieved the primary functionality of the resource pack functionality. So with that, I'm going to go ahead and call this video there. Again, I know it's long and I'm not going to continuously apologize for rambling. I feel like everything that I've talked about has been fairly important. And I hope that you have learned something from the various demonstrations and the things that we've talked about. Next episodes, we'll be talking about the encryption, which again is going to be, we're really only going to be talking about the encryption in the next episode because the actual reading and writing of the files is all going to be the same. So we're not going to be duplicating that content. With all that said, I hope you have a wonderful day. Have a happy holiday, and I will catch you all next time. Bye-bye.